the office hours. In this episode, we're going to be learning about troubleshooting Ospf neighbor adjacencies from NetworkLessons.com. Doesn't look like this lesson has a lab, so I'm just going to be reading through it. This lesson covers Ospf and all the different things that could possibly go wrong. Ospf is, unlike EIGRP, a link state protocol, but what they share in common is that both routing protocols establish a neighbor adjacency before exchanging routing information. In the case of Ospf, we are exchanging LSAs in order to build a link state database. The best information from the LSDB will be copied over to the routing table. In this lesson, we'll be troubleshooting the Ospf neighbor adjacencies. Once we have a working Ospf neighbor adjacency, we can look at other issues like missing routes. When looking at the Ospf neighbor adjacency, this is what we like to see. So we have R1. It's looking at R2, which by convention ends in .2 in its lessons, and it's changing from loading to full. And over here, when we do a show IP Ospf neighbor, the state is full, and R2 appears to be the designated router. Typically, we want to see full here when we look at our neighbors. There is one exception to the rule. When we use a DR-BDR, then two normal non-DR or non-BDR Ospf routers will not form full adjacencies with each other. They will remain in a two-way state. When the Ospf neighbor adjacency is not in the full state, then it's in one of the following states. It's either there's no Ospf neighbor at all, it's stuck in a temp, it's stuck in init, it's stuck in two-way, or start, exchange, or loading. Let's take a look at some of the different issues as to why we can't form the Ospf neighbor adjacency. So moving on to Ospf network command. Looks like we have a topology where we have R1 and R2 that are connected via a single link, and these two links are in Ospf area 0. And the problem we have is that they aren't becoming neighbors. So if we look at R1 and we do a show IP Ospf neighbor, we're going to see nothing. As you see, we don't have any Ospf neighbors. So what could be wrong? The first thing he's doing is he's doing a show IP Ospf interface fast Ethernet 0/0, and it doesn't look like Ospf is enabled on this interface. So what do? We go to R2 and we verify the same thing, and it looks like R2 is fine. It's running Ospf on fast Ethernet 0/0. The author says, I could just look at the running configurations and see what's wrong, but I want to show you some useful Ospf commands. First, I'll use show IP Ospf interface. We can see that Ospf is not enabled on fast Ethernet 0/0 of R1, but it's running on R2. Let's take a look at the configurations for R1. So over at R1, we see that we're using the network statement on 192.168.121 with a wildcard mask of 0.0.0.255, but I kind of already spotted the issue, because this network statement should be 192.168.12.0, right? Because in the topology in the diagram right here, this is the network that we are using. So there appears to be a typo with this network statement. So it looks like the author goes in and he fixes that. He does a no command on the network statement, and then he reissues the network statement with the correct IP and wildcard mask. So after that, it looks like it's in full state, and router 2 has become the designated router. So what is the lesson learned? Make sure you have configured the correct network address, wildcard bits, and area. All right, let's move on to the next issue. So we have OSPF passive interface, and we have the same topology, and we're looking at R1. And it looks like when we do show IP OSPF interface fast Ethernet 0/0, looks like there's no hellos because it's set as a passive interface. OSPF has been enabled on the interface of both routers, so we know that the correct network type was used. However, if we look closely at R1, you can see that it says no hello passive interface. If you configure passive interface, then the network on this interface will still be advertised, but it won't send any hello packets. This way, it's impossible to form OSPF neighbor adjacency. And if we take a look at router 1's configuration, looks like we passive out fast Ethernet 0/0. So if we do a no statement on this, that should fix the issue. And the lesson learned here is that we make sure that OSPF is sending hello packets on an interface, because otherwise you won't become neighbors. All right, moving on. OSPF multicast filtering. We say we're using the same topology, and in R1, the author issues a show IP OSPF neighbor, and we see that R2 is currently in init and init state, while it's being considered as a druther, so neither a DR or a BDR. Then we go to R2 and we do a show IP OSPF neighbor, and we don't see any results. And he's saying R1 is showing our OSPF neighbor to be in init state, while R2 is showing nothing. So looking at the interfaces, we see that we do have OSPF enabled on both interfaces. OSPF has been configured properly on both interfaces, as we can see in the example above. Since R1 is showing the init state, we can draw the conclusion that it's receiving something from R2. R2 isn't showing anything, so it's probably not receiving anything from R1. OSPF uses hello packets to establish OSPF neighbor adjacencies, and these are sent to the 224.0.0.5 multicast address. Let's see if this address is reachable. So over at R1, we're going to do a ping to this multicast address, and it doesn't look like we're getting a response. Same with R2. It's a good idea to check if we can ping the multicast address that OSPF uses for the hello packets. We can see that both R1 and R2 aren't getting a response. What about unicast traffic? The R1 and R2 are pinging each other. Looks like there's a success. Pinging the IP addresses of each other is no problem. So what could cause an issue of sending and receiving OSPF multicast traffic? How about an accessless? So over at R1, we don't have any outbound and inbound accessless that are applied, but for R2, looks like we do have an accessless called block stuff that is referenced here. And what this accessless states is that it'll permit any TCP, any UDP, but for any ICMP, wait a second, it's all permits. So what's the problem? The access list is only permitting TCP, UDP, and ICMP, but OSPF doesn't use any of these three, right? Yeah, because there's an implicit deny any at the very bottom. You don't see it but there's always a deny at the bottom of an access list. Let's change the access list so that OSPF traffic is allowed. And so we're going to edit that block stuff access list, and we're going to put a sequence number of 5. We're going to permit it, and it'll be Ospf any, and that should allow R1 and R2 to become neighbors. And if you try to do a ping on the multicast address now, it looks like it'll work. It'll get a reply from R2, and R2 will get a reply from R1. These pings are now working. This is nice and a quick method to check if multicast traffic is blocked or not. Anyway, our problem is solved. The lesson learned here is don't block Ospf multicast addresses 224.0.0.5 and .6. Next, we have Ospf subnet mask. Once again, we have this topology, and on R1 and R2, the thing is showing up as on the neighbor table when we do a show IP Ospf neighbor. Of course, we're going to check the multicast address and see if there is a response. It looks like there is or there isn't. Okay, there is, because we see router 2's IP address right there. And over here we see router 1's IP address. The author says I can ping the multicast address, so that's no problem. This might be a good moment to enable debug to see what's going on. So over at R1, he enables debug, and he resets Ospf, which probably isn't a good idea in production. I'll reset Ospf to speed things up. Keep in mind, you can also reset just one Ospf neighbor, which is a better idea in a production network. Here's what you will see. In R1, we see that there are mismatch hello parameters from R2. So it's like the mask we see is a /25. Now we have something to work with. R1 says it received a hello packet, but we have a mismatch hello parameter. The R stands for what we received, and the C stands for what we have configured. So dead timer R40, C40, that's correct. Hello timer R10, C10, that's right. The mask, we received a /25 while we have configured a /24. So that appears to be the problem. Moving on, we check the configurations or the Ospf for Fast Ethernet 0/0. We see a /24 here, but over at R2 we see a /25, so that's going to be a problem. Alright, let's change the subnet mask of R2. Pretty self-explanatory, and the lesson learned here is make sure you have the same subnet mask on routers that are directly connected to each other. Alright, I'm going to take a short break to check something. Alright, Ospf hello and dead intervals. The next issue is also related to hello packets. We have the same topology here, and over at R1 we've enabled debug for Ospf hello. and we see a message that says mismatched hello parameters. And what's mismatched is for the dead timer, we received 11, but we ourselves have configured 24. And same with the hello, we received 10 while we have configured 6. So how do we fix this? We go to R1 and we do an IP Ospf hello interval to 10. To 10 so that we can match R2. And then for the dead interval, we change it to 11 to match R2. After that, it'll come up as full, and R2 is recognized as the DR. The lesson learned is make sure the required parameters match. The next issue we could possibly come across is Ospf authentication. Alright, so R1 and R2, if you try to look at the Ospf neighbor, doesn't show up as anything. And if we do a debug on R1, we see an error that says there's a mismatch authentication type. Input packet specified type 2, we use type 0. So on R1, doesn't look like there's any authentication being used, but on R2, an MD5 authentication is being used. On R2, if we do a show IP Ospf interface fast Ethernet 00, and we do a pipe include authentication, we see that message digest authentication is enabled. And if we do a show run interface fast Ethernet 0/0 and we include Ospf, we see that we do have a key here, and we just need to apply this statement and also this statement over at R1 on its fast Ethernet 0/0 interface, and the relationship should come up, or the adjacency should come up. In case you are wondering, what do we see when we have a password mismatch? So what we would see is that there's a mismatch authentication key. Our debug is nice enough to tell that we are using the wrong key between our routers. The lesson learned here is that make sure you use the same Ospf authentication type and make sure the passwords are typed in correctly on both sides. Alright, next subsection, which is Ospf area mismatch. Same topology, but looks like on R1 we configured area 0, but it's seeing, I'm sorry, on R1 it looks like on fast Ethernet 00 we have configured it to be in area 1, while on R2 it's in area 0. So yeah, that's going to be a problem. And the fix is pretty self-explanatory, so I'm just going to move ahead. That's way too simple. We have Ospf area type mismatch. What does this mean? Same topology. The author turned on debug mode, and on R1 it's seeing a hello from R2 with a mismatch stub transit area option bit. Ospf has different area types, and both routes have to agree on the area type, either stub and NSSA, totally stub, and totally not so stubby area. Let's see what's configured. So for R1, the number of areas in this router is 1 space normal, 0 stub, 0 NSSA. R1 seems to be configured to use a normal area. What about R2? R2 seems to be using a stub. R2 seems to be configured to use a stub area. A mismatch in the area type means we can't establish an Ospf neighbor adjacency. So if we go to R2, we'll see that it has the global command in the router configurations. And that line is area 1 stub. Here you can see that R2 has the area 1 stub command. If you get rid of it, that should bring up the adjacency, but I thought they were both on area 0. No, they're actually both on area 1. So that looks like it's correct. Alright, so we have OSPFDR, BDR election, and same topology with area 1. So let's see. What was it? Was it the higher IP address that wins the election if the priorities are the same? So in that case, wouldn't R2 win in this case? We're gonna have an empty OSPF neighbor. Wait, what? So both routers are stuck in two-way state. Besides focusing your eyes looking for the word full, there are two things you should look at in the show statement. Both routers show as druther. The priority is 0 for both of them. On a multi-access network like Ethernet OSPF, they'll do a DR-BDR election if the network type is broadcast or non-broadcast. So if we verify, we're going to see that the network type is broadcast on both routers. Both interfaces are configured for the broadcast network type. This is the default for Ethernet interfaces. This means we have a DR-BDR election, but both routers are configured for priority 0, which means they won't participate in the DR-BDR election. This is the reason they are stuck in the two-way state. We can fix this by giving R1 a priority of 1. And in that case, R1 becomes the designated router while R2 remains as druther. Lesson learned. The broadcast and non-broadcast network types require a DR-BDR election. Make sure one of the routers gets elected. I thought there was a tiebreaker if the priorities were the same. Let me actually go back and figure out how it's actually done. DR election. Let's see if there's something I can use here. Alright, ties among routers with equal DR priorities are broken by router ID, with the highest router ID being preferred. Yeah, I thought so. Going back. Alright, where were we? Oops. Yeah, we were here. And, for the broadcast and non-broadcast network types, for the broadcast and non-broadcast network types require a DR-BDR election. Make sure one of the routers get elected. Okay. So the next subsection is Ospf network type. Looks like we have a new topology where we have a frame relay being used. For some reason, Ospf isn't establishing the neighbor adjacency. So we have router 1 that's putting its interface in area 0, and so is R2. They're pingable, but if we try to ping the multicast address, it seems to work as well. I'm able to ping the Ospf multicast address. This proves that broadcast capabilities for frame relay have been enabled. I can verify this by looking at the frame relay maps. Okay. The keyword broadcast means that we can send broadcast and multicast traffic down the PVC. If you studied CCNP route, you might recall that Ospf has different types of networks. So broadcast, non-broadcast, point to multipoint, point to multipoint, point to multipoint non-broadcast, and point to point. What Ospf network type is default for frame relay interface? If we take a look below, it looks like the default is a non-broadcast. This means that Ospf expects us to configure the neighbors ourselves. So we can do that with this configuration. So on R1, we do a global command, specify that the neighbor will be the IP address of R2, vice versa with R2. And once we do that, it looks like the adjacencies have formed. And as soon as we do this, our Ospf neighbor adjacencies is working. Any other ways to fix this? Of course, it's also possible to change the Ospf network type. So alternatively, you can go to the interface that's being used for Ospf, and inside the interface, you would use the statement IP Ospf network broadcast, and that should also fix the issue. Make sure you understand all Ospf network types and their requirements. These are the issues I wanted to show you with Ospf neighbor adjacencies. There's quite some stuff that could go wrong, but you've seen that I mostly use the same commands to spot these errors. So these are commands, and that looks like it's it. So I'm going to stop here and start up another stream for the next lesson, which looks like it's going to be for Ospf non-broadcast network type. Thank you for watching.